Alrighty, folks. So moving along to chapter 11, lesson 2 here, we're going to be talking and introducing the idea today of the electric potential difference, also known as the voltage, which is probably a term you've heard before, right? Voltage, you see it on batteries and stuff like that. We're going to talk about what it actually means today, okay? Now they are two names. They mean the exact same thing. They're used interchangeably. Personally, I actually prefer this term, the electric potential difference. I think once you learn what it is, you will probably agree with me because this is a little more descriptive. This is actually talking about what it means. Okay, whereas voltage is just, we wanted to name something for a scientist, so we called it the voltage, named after Volta, the scientist, okay? But anyway, we're going to start out here like we did with electric fields, okay? And as you saw with electric fields, because there are so many conceptual similarities between electric fields and gravitational fields are often a good way to kind of start thinking about these because you know gravitational fields, you studied them in physics 20, and you experience them every day. You're kind of comfortable with how gravity acts a little bit more, right? So we're going to do a similar thing here with the voltage. To think about the electric potential difference, we're going to start by thinking about the equivalent concept in the gravitational field. Okay. Now, again, it's not too surprising that electric fields and gravitational fields have so much in common. They really, at the end of the day, are describing very similar things. They're both talking about the amount of force an object would feel, if placed at a given location. It's just that for the electric field, that force is an electric force that it would feel because of its charge. For the gravitational field, that force is a gravitational force that it would feel because of its mass. Okay, so let's start building up some of these concepts by thinking about the gravitational field first. Okay, so a massive object, that just means something with mass, that's in a gravitational field has the potential to move if dropped, right? If you're holding an apple, it has the potential to move. All you have to do is let it fall, and the Earth's gravitational field will cause it to move, right? Pull it downwards. So we studied this in Physics 20, and even in Science 10 you looked at it. This is the idea of gravitational potential energy, right? If you have an apple in your hand and you drop it, that gravitational potential energy gets converted into kinetic energy, right? So that energy is not created or destroyed. So when you drop it and it starts moving, you know it's getting kinetic energy. Well, energy can't come from nowhere. It's that gravitational potential energy it had because of its height within a gravitational field that then gets converted into that kinetic energy as it falls, right? As it falls, we know it's losing gravitational potential energy, and therefore it's not just disappearing, that gravitational potential energy, it's being converted into kinetic energy as it moves faster and faster. And so as you learned in Physics 20, right, the equation for gravitational potential energy is just the object's mass times the gravitational field that it's in. Sometimes we call that acceleration due to gravity since they're always the same number, times however high it is above the height that we're calling zero, right? Recall that gravitational potential energy is only meaningful when we're saying compared to somewhere else, right? How much energy would something gain or lose in terms of kinetic or potential if it were to fall from this place to a height that we're calling zero, okay? So you can see up here, right? Up here it has a high amount of gravitational potential energy, EP equals mgh. Now if it were to fall, that energy wouldn't be destroyed. You can see that it would lose potential energy though, right? Its height would be decreasing, and so it would be losing potential energy. But that's not just disappearing, because we know energy can't be destroyed. It's being converted into kinetic energy, which again, we've used that equation in Physics 30, but you also looked at it a lot in Physics 20, 1/2 mv squared, right? So it's losing height and therefore potential energy, but as a result, it's gaining speed and therefore kinetic energy. Okay, so again, if it is at some height in a gravitational field, it has gravitational potential energy. If we were then to take this mass and move it to a higher height, right, it would now have a different amount of gravitational potential energy, right? Hopefully that's not too shocking, right? If we took this and we applied some external force to it and moved it to a different height, we'd be changing its gravitational potential energy. We'd have to be, because part of that calculation involves the height it's at. So if it were moved to a higher position, it would now have a different amount of potential energy. And remember, whenever there's a change in energy that occurs, we say that work has been done on the object, right? Don't forget, work is nothing more than a change in energy. The amount of work done on an object is how much its energy was changed by. So if we were to take this and move it so that it gained 100 joules of potential energy, we would say that we had done 100 joules worth of work on that object. Just writing it out, right? Work is the change in energy. Change in anything is final minus initial. So the final potential energy would be mg times the final height, the initial mg times the initial height. And if we pull out mg as a common factor, we realize this is just mg times h final minus h initial, or mg times the change in height. Okay, so again, all we're thinking about so far is that if we have a ball with mass and we move it to a different height, we will have changed its potential energy. Now, what I want to start thinking about is how much the change in energy is and what that depends on, okay? Again, we're starting out by talking about the gravitational potential energy and gravitational fields here, but a lot of these same ideas are going to carry over when we look at electric potential energy and electric fields. So, we can see from the equation here, right, what it depends on. Well, one of the big things, right, if I were to lift it from here to here versus lifting it from here to here, right? Obviously, I would give it a different amount of potential energy if I lift it higher than if I don't lift it as high. So definitely the change in height, right? That's part of the relationship here. If I lift it higher, I could change its energy more and therefore have done more work. That's one way to do more work, right? But another way we could have done more work is if this object had more mass, right? So even if I lift it to some new height that's up here, okay, even if I lift it to the same height, if I take a different object with more mass and do the same thing, we can see that the change in potential energy would be even larger, right? Because again, it has more potential energy here, it has more potential energy here, so a bigger mass gets a bigger change in energy even if we lift it to the same height. It's in the equation there. Okay, so the mass of the object is also important. And the last piece of the puzzle here, the last piece of our equation is G, the gravitational field. Again, we sometimes call that the acceleration due to gravity. That's because they're always the same number. But again, it's the same as the gravitational field that it's in, right? Near the surface of the Earth, it's 9.81 newtons per kilogram. It will feel 9.81 newtons of force for every kilogram of mass it has. So again, if it were in a stronger gravitational field, it would take more work to move it from here to here, right? If we did the same experiment on Jupiter, even if we lift it the same height and even if it has the same mass, if it's in a stronger gravitational field, that will require more work, right? Imagine lifting something on Jupiter. It would require more energy out of you than lifting something on Earth. So it also depends on the strength of the gravitational field that it's being moved through. And really, the equation told us all of that, okay? But we're just thinking through this, right? To move something within a gravitational field, to take something in the gravitational field and move it to another position in the gravitational field is going to require work, right? We're going to be changing its energy. How much we have to change its energy by, and therefore how much work we have to do that, depends on how massive the object is, the strength of the gravitational field we're in, and how high we actually want to lift it, how much we want to change its height by. Okay, now we're going to start thinking about something here, okay? First, let me just explain what you're looking at here, right? Recognize that number. So what I'm drawing here is the Earth, right? Or at least like the surface of the Earth as viewed from when we're pretty close to it. Okay, now we know that close to the surface of the Earth, the gravitational field strength is 9.81 newtons per kilogram. meaning 1 kilogram of mass feels that many newtons of force because of Earth's gravitational influence. Now, technically, Earth's gravitational field is not uniform. You know that, right? Uniform meaning it's not the same everywhere. We know that as we move further away from the center of the Earth, the gravitational field gets weaker. But if we're zoomed this far in to where we're just looking, for all intents and purposes, the gravitational field is essentially uniform. Technically, the gravitational field is a little bit weaker up here than it is down here, okay? But if we're talking like a difference in distance of like even as tall as a skyscraper, right? The amount of difference in the gravitational field strength because of changes in height like that is basically zero. Like it might be 9.809999999999 instead of 9.81, okay? So it's basically the same. Close to the surface of the Earth, it is essentially a uniform field. Now, what we're going to start talking about here, and what I want you to start thinking about, is how could we kind of generalize a way to talk about the difference in potential energy, the difference in gravitational potential energy between, say, this position here and this position here. So between these two heights, right, can we come up with a way to talk about the amount of change in potential energy an object would experience if going from here to here, this height to this height, or this height to this height? What would be the associated change in gravitational potential energy? And just for the sake of being able to put in some numbers to think about it, let's just say that it's a change in height. The difference in height between these two positions is 1 meter. Okay, so what I'm asking here is, can we come up with a general way to talk about how an object's potential energy would change if moved from here to here, or vice versa, from here to here, right? If it was moved 1 meter in this 9.81 Newton per kilogram gravitational field. And you realize it's almost frustrating, isn't it? Because we're so close to being able to say what its change in potential energy is, right? We've shown that it's just mass times the gravitational field strength times the change in height. We know we're talking about a difference in height of 1 meter. We know we're in a gravitational field strength of this strength, 9.81 newtons per kilogram. The only problem is the only reason we can't talk about how much gravitational potential energy an object would gain or lose by moving between these two positions is that, well, objects of different mass would gain or lose a different amount of potential energy, right? If it has 1 kilogram of mass, it'll gain half as much potential energy as a 2 kilogram mass would from going here to here, right? An apple would gain a different amount of potential energy by moving from here to here than an elephant would, right? But it's so close, like it's just, we know that it really just depends on this and how high we're moving it. So we're so close to talking about the amount of potential energy that it would gain or lose by moving from this position to that position or vice versa. We just can't actually say how much gravitational potential energy because it could be any mass, right? But can we come up with a way to work around that? Because again, we're getting at the core idea here, right? It just depends on how many kilograms of mass it has for the change in potential energy. But other than that, to move 1 meter this way in this gravitational field, right, the change in potential energy is basically set. It's just that something, again, with 5 kilograms of mass will gain 5 times more potential energy than something with 1 kilogram of mass. And so what we can essentially do to get around that is to just say, okay, well then how much potential energy will it gain or lose by moving between these two positions for every kilogram of mass that it has? What will be its change in energy per kilogram of mass that it has, right? And there we go. Now we can still come up with a way to think about the difference in potential energy between these two positions, even though we're not necessarily even moving a real mass between these two positions. We all know it has a different amount of potential energy here than it does here, no matter what the object is. And now we can come up with a way to describe that. We just say, okay, so per kilogram of mass that it has, its energy will change by this much. Essentially what we're doing is saying the change in energy per kilogram, will just be equal to the gravitational field strength times how far you want to move it through that gravitational field. And so that's what this section of the notes here is explaining, right, and talking about. So even if we don't know the mass of the object being moved, or really, even if we're not even actually going to be moving a mass of any real object at all, right, we could still generalize the difference in the potential energies between two different heights by thinking about the energy difference per kilogram of mass for any object being moved, right? What we're essentially saying there is per kilogram of mass that it has, how much work, how much change in energy needs to happen to move something between these two positions, right? Again, per kilogram of mass that it has, how much potential energy would it gain or lose by moving between these two positions? Right? And that's what we're saying here. Now notice here something important that you did talk about in Physics 20. It is about a difference, and differences inherently are a comparison. They require another place that we're comparing to, right? If I were to ask you, what is the object's change in potential energy here? You would say, well, what do you mean? Compared to where, right? I'm talking about a change in potential energy. So you would say, well, compared to down here, I could think about it, but you can't just ask me what's its change in potential energy at one position, right? Inherently, this is a comparison. Gravitational potential energy and changes in potential energy inherently require us to say compared to some other place. We're talking about, again, a difference, right? What is the difference in potential energy for it to move between two positions, okay? And so by doing this, by thinking about how much potential energy would it gain or lose by moving between these two positions per kilogram of mass that it has, we can talk about the difference in potential energy between two different points in a gravitational field. Even if we're not actually moving a real mass, we can still say, well, if we did, for every kilogram of mass that it had, it would gain or lose this many joules of energy by moving from position 1 to position 2. You'll notice, what are the units of this quantity we're kind of talking about? Well, energy is measured in joules per mass is measured in kilograms, right? So doesn't that make sense? We were talking about the amount of energy change it would have for every kilogram of mass that it had. So this quantity would be measured in joules per kilogram, okay? Now, we call this quantity, the one we're talking about here, whether it's the change in potential energy over m or acceleration due to gravity or gravitational field strength times the change in height that actually occurs, okay? We call this quantity, it does have a name, it's the gravitational potential difference. Good name, right? We're talking about the difference in potential energy between two positions because of a gravitational field that we're moving it through. Now, we don't focus on it very much in Physics 20, and to be honest, it doesn't come up that much in general, but it's really helpful to think about it and for conceptualizing what its equivalent or its analog in the electric field is. So here we go. We're going to take all of those ideas, everything we just talked about, and now we're just going to think about, all right, but what if it's not feeling a gravitational force because it's in a gravitational field? What if we're thinking about something that could be experiencing an electric force because it's in an electric field? Same concepts, fields and forces, it's just the reason for the field or the reason for the force that we're changing to electric phenomena now. Okay, so now notice how similar the ideas are, okay? We said that a massive object in a gravitational field has the potential to move if dropped, right? It has gravitational potential energy. Well, guess what? A charged object in an electric field has the potential to move if released. It has electrical potential energy. If we released it, that electrical potential energy would be converted to kinetic energy, right? Just like if we dropped our mass in a gravitational field, that gravitational potential energy would be converted into kinetic energy. Okay, same idea here. Look at this charge. It is in an electric field. We can tell that the electric field would look like this. Remember, electric field is always what the direction that a positive test charge would feel a force, right? So a positive charge would want to move away from this positively charged plate because like repel. And furthermore, it would like to move towards this negatively charged plate because opposites attract. So do you see what I mean, right? If you had this charge here and you let it go, that would shoot towards this plate. It would get a whole bunch of kinetic energy. It would get moving really fast, right? Well, that kinetic energy can't have come from nowhere. So where did it come from? Electrical potential energy. It's the exact same idea, right? It's just the reason for this potential energy, the reason it could gain kinetic energy is not because of gravitational forces and gravitational interactions, it's because of electrical interactions. But for all intents and purposes, electric potential energy and gravitational potential energy are essentially the same thing. They just have different causes, right? Different root sources. And so just like dropping the mass, dropping an apple, right? The same thing's happening here. It's just not gravity that would be causing the conversion of potential energy into kinetic. It's electricity, electrical interactions, okay? So it would have a lot of electric potential energy up here. It would want to move to there, okay? Just like a mass would want to fall through a gravitational field. Now, just like we said with the mass and gravity, what if I were to take this charge and move it to here? Would it have a different amount of electric potential energy there, right? If I were to take it and move it to a different position? Well, yeah, right? It's not going to be able, if I were to, lower it down to this position and then hold it there before releasing it, it wouldn't gain as much kinetic energy by going from here to this position as it would have by going from here to this position. In other words, we could say there is a difference in the potential energy an object would have here versus here, right? There's a difference in potential energy associated with moving between these two positions, right? See how similar these ideas are? So if a charged object were moved to a different position, where it would gain a different amount of kinetic energy if released, then it would have a different amount of electric potential energy. And work would have been done on it. Whenever you change something's energy, you have done work on it. Remember, work is just a change in energy. Now, how much work and how big the change in energy is going to depend on a couple things, right? To go from this position to this position, how big of a change of energy that represents? Well, it's going to depend on, firstly, how big of a change in position are we talking, right? The difference between the potential energy it has here versus here is obviously different than the change in potential energy it would have here versus here, right? By going from here to here, we'd be taking away less potential energy than if we were to move it from here all the way to down here. So it depends on the distance that the charge is actually being moved through, right? In other words, the distance between the two places that we're comparing. It's also going to depend on how much charge this has, right? Does it have 1 nanocoulomb of charge or does it have a coulomb of charge? That's going to involve a very different amount of potential energy because we know, right, the forces it feels depend on its charge when it's in an electric field, right? The electric field is newtons per coulomb of charge. So if it has more coulombs of charge, if it's a more concentrated charge, it's going to be feeling bigger forces. We're going to be dealing with bigger changes in energy. So the magnitude of the charge being moved. And to go back and connect this back with gravity once again, right? The mass of the object, it was a similar reasoning. To lift this from this position to this position would be a bigger change in energy if it had more mass. Yes, because of this equation, but we could also connect it to the fact that it would be experiencing a bigger force of gravity, right? And don't forget as well, yes, work is a change in energy, but it's also the force you have to apply times the distance you apply it for. So bigger forces, right? If we're fighting bigger forces, we are giving it more potential energy. We're doing more work. And just a reminder again, those are both on your formula sheet as well. Work is just a change in energy, and work is equal to force times distance times the cosine of theta. The cosine of theta being there because we're only doing work when we're actually moving it like this, right? If I were to take an object and move it from here to here, I haven't changed its energy, so I haven't done any work on it, right? But if I move it from here to here, now I've changed its potential energy. I've done work on it. We'll circle back to that idea as we go, okay? And the last thing it would depend on is the strength of the electric field that it's being moved through, right? Again, for similar reasons. If this is a very, very strong electric field, we're talking about different amounts of potential energy, right? It could gain a ton of kinetic energy if this is a very strong electric field. If it's a very weak electric field, it'll still gain kinetic energy by being allowed to drop from there to there, but not as much as it would in a strong electric field with larger forces per coulomb of charge, and therefore bigger accelerations, bigger speeds, bigger kinetic energies. So again, folks, notice here, right, the near identical nature of these two sets of ideas, right? The amount of gravitational potential energy it could gain or lose by moving from one position to another depended on how far apart those two positions were, right? Well, same thing here. The amount of electric potential energy it could gain or lose by moving from one position to another depends on how far apart those two positions are, right? The strength of the gravitational field. In a stronger gravitational field, there's bigger changes in energy associated with moving between two positions. Well, the strength of the electric field, right? Stronger electric field means there's a bigger change in energy to go from one position to another, okay? And then the mass of the object versus the charge of the object, which isn't too shocking. We know mass is what generates gravitational fields. Mass is what allows things to feel a gravitational force. Well, charge is what allows things to feel an electric force, right? These really are the same ideas. It's just mass causes gravitational stuff to happen. Charge causes electrical stuff to happen. Other than that, all the basic physics principles and concepts going on there are identical. Now, here we go. I'm going to ask you a very similar question to what I asked about before, right? Can we come up with a way of thinking about the difference in electric potential energy associated with this position, say, versus this position, right? So at this distance from the positive plate and negative plate, and at this distance from the positive and the negative plate, okay? In fact, just to give it numbers, let's say once again that they are 1 meter apart. So I'm going to call it a distance because it's not necessarily a height anymore, but same idea. A height is just a distance that means upward distance, right? So these two positions are separated by 1 meter. They're in an electric field, okay? And just to give it numbers, I said the electric field was 10 newtons per coulomb, meaning that for every coulomb of charge something has, if we put it in here, it will feel 10 newtons of force. Now, once again, it's almost frustrating, isn't it? Because we know basically everything we need to know about these two positions. We know the strength of the electric field that we're moving through, right? We know the distance that those two positions are apart. We know, like, really all the important stuff about these two positions, but the problem is a 1 coulomb charge and a 2 coulomb charge would gain different amounts of energy by moving from here to here or from here to here, right? So do you see how we're walking down the same path we walked around here before, right? Couldn't we come up with a way to talk about how many joules of energy it would gain or lose per coulomb of charge that it has by moving from this position to this position? And then we just know that, all right, well, if it's a 2 coulomb charge, we'll gain twice as much energy or lose twice as much energy by moving between these two positions, right? A 0.5 coulomb charge will lose half as much energy as a 1 coulomb charge, right? We have found a way, just like we did up here, to generalize the difference in potential energy between these two positions, even without having a real charge that we're moving through there, right? Because again, that was all we were missing was, it's so close. We know everything we need to know about this position and this position. The only thing we don't know is how big is the charge we're actually moving. So let's not worry about that and say how many joules of energy would it gain or lose per every coulomb of charge that it has, right? And now we can talk about the difference in potential energy here versus here. It's just the difference in potential energy per coulomb of charge. So, summarizing that idea here, right? Even if we don't know the charge on the object, or again, even if there's not actually a real object at all that's being moved through the field, we can still generalize the difference in the associated potential energies between 2 points. Again, this is fundamentally a comparison between 2 points. What's the difference in potential energy? In an electric field by thinking about the energy difference per coulomb of charge on the object being moved, right? We're essentially saying or asking per coulomb of charge that it has, how much work needs to be done to move something between these 2 positions. Or in other words, per coulomb of charge that it has, how much potential energy would an object gain or lose by moving between these 2 positions. And this has its name, this quantity of how many joules would it gain or lose per coulomb of charge, okay, by moving between these 2 different points. The difference in potential energy between 2 different points in an electric field per unit charge is known as the electric potential difference, or the voltage. So do you see what I mean, right? Why this name is actually kind of a better name, and I wish we used that, but voltage is what's commonly used on like packages for batteries and stuff, right? But electric potential difference tells you so much more about what it is. It's the difference in electric potential energy between 2 positions. It is a difference, right? It is fundamentally a comparison. It's saying what's the difference in electric potential energy per coulomb of charge between these 2 positions. So when you see that, for example, a battery is, 9 volts, right? You've got a 9-volt battery. And this is a bit of an oversimplification, but it's the basic idea. How batteries work is they essentially have a negative terminal and a positive terminal. Negative electrons are stored, and they want to get away from the negative terminal. They want to move towards the positive terminal. So when you hook it up to a circuit, maybe that circuit's got a light bulb in it. What that 9 volts means is that the difference in the potential energy of charges here versus here, if we allowed them to move from here to here, how they would like to move, the same way how this would like to move from here to here, or the mass would like to fall towards the earth, quote unquote, right? What this 9 volts means is that for every coulomb of charge, it will, in this case, lose 9 joules of potential energy. So a volt is actually a joule per coulomb. A volt is another example of a derived unit, right? Just like the Newton was really a kilogram meter per second squared, a joule per coulomb is a volt. Now, I much prefer the unit joules per coulomb. Doesn't that tell you so much more about what it actually means than a volt, right? This is another case of we wanted to name something after the scientist Volta, so we gave him voltage, right? But really, a joule per coulomb is such a better way to think about it, right? For every coulomb of charge, it will change its potential energy if allowed to go from here to here by 9 joules, right? So an electron doesn't have 1 coulomb of charge. We know it has 1.6 times 10 to the negative 19 coulombs of charge, right? But we could figure out how much potential energy an electron would lose by going from here to here by now taking its charge and multiplying it by the number of joules it will lose for every coulomb of charge it has. And that's what a 9-volt battery means. It means for every coulomb of charge, they will lose 9 joules of potential energy by going from here to here. That's the potential difference between the terminals of the battery. The difference in electric potential energy for a charge here versus here, right? Hook it up to a light bulb and you can use some of that energy that it's losing along the way to create light energy, right? And heat energy and all that fun stuff. Okay, so just to really drive it home, notice we call this the electric potential difference. We called this one the gravitational potential difference. They really are the same idea. It's just a different type of field, a different type of force that's at play. But all the concepts fundamentally are the same. Okay, so electric potential difference and voltage, these are synonyms. They mean the exact same thing. Personally, I prefer this terminology because it tells you what it means, right? Though voltage is probably the more commonly used, okay, this to me gets at what it really means. Same goes for the units. Volts in our day-to-day are more commonly used, but joules per coulomb, to me, that really gets at what it's saying, what it means, which is to move between these two positions, how many joules of energy will you change by for every coulomb of charge that you have? So if the voltage between these two plates is 10 volts, that just means that a 1 coulomb charge would change its energy by 10 joules by being moved from here to here. A 2 coulomb charge would change its energy by 20 joules. A 0.5 coulomb charge would change its energy by 5 joules. That's all that means. It's a way of comparing two positions in terms of the difference in potential energy for a charge moved between those two positions. The electric potential difference. Now again, remember, work is a change in energy, right? It's energy final minus an energy initial. And all of this stuff we're talking about is about changes in energy, okay? So we need to use delta notation, right? Again, none of this makes any sense without saying what's the difference in potential energy between these two positions, okay? So here is the equation, and you probably have worked this out if you've been, following along here, okay? The voltage, and yes, it does come by default with that delta, that change in, because it's a difference in two positions. So the voltage, is equal to the change in energy per unit charge, right? Just like we talked about the gravitational potential difference being the change in potential energy per unit of mass, right? Per 1 kilogram of mass. The voltage, the electric potential difference, is the change in potential energy between two positions per coulomb of charge that's being moved between those two positions. So whenever we get a new formula, it's always good to go find it on the formula sheet. Okay, we are in electricity and magnetism, and so sure enough, there it is. The voltage, aka the electric potential difference, is equal to the difference in energy between two positions divided by the charge that's being moved between those two positions. Now, we already talked about this, but now the equation can have our back a bit here, right? What is an equivalent unit for the volt? Has symbol V. Well, a volt is equal to energy is measured in joules, charge is measured in coulombs, so 1 volt is just 1 joule per coulomb. And like I said, to me, this is a much better way to think about it. You will pretty much mostly see me write it this way. I will use volts just so you're comfortable with them, and when you see them on a quiz or a test or a diploma, you don't freak out and say, what's the V? But personally, I always write it as joules per coulomb because that makes way more sense to me. I can think about what it's saying. It's not just named after some guy for the sake of being named after some guy. Okay, so just a little heads up before we take this new equation for a spin, okay? The change in energy we're interested in here is pretty much always going to be from electric potential into kinetic energy, okay? Or vice versa, from kinetic into electric potential, right? Again, nothing too shocking here. You drop the ball in the gravitational field, its gravitational potential energy is converted into kinetic as it falls, or vice versa. You could throw the ball upwards, give it a lot of kinetic energy at the beginning, and that kinetic energy slowly gets converted into gravitational potential, right? It's moving fast, it gets slower and slower and slower as its kinetic is converted into potential, right? It's gaining height, so it's gaining potential energy. Same thing, but in reverse, right? You could also drop it so that it's moving fast there. Okay, for electric potential energy conversions, same idea. You could have a, charged plate here and a charge, and maybe they accelerate towards each other because of the electric potential energy being converted into kinetic energy. But you could also have, a charged plate here that's actually repelling your charge. It's moving very fast up here, and that gets converted into electric potential energy, bringing it to a stop until it turns around and the whole process repeats. Then that potential turns back into kinetic, right? The same way when you throw the ball up in the air, that kinetic initial is converted into potential up here, but then what's it going to do? It's going to come back down again and convert that potential back into kinetic. Okay, anyway, all of this to say, typically the energy change we're looking at in any of these questions is going to be between kinetic and potential. That's the energy change that's often happening. So we will very often use physics principle number 3, which is the work energy theorem, right? And again, all the work energy theorem says is that work is equal to a change in energy. So if you know how much you've changed an object's energy by, you know the work you've done on it, right? Or physics principle number 5, which is the law of conservation of energy. That is just saying that total energy initial equals total energy final. So if you know that it has potential energy originally, and that's going to be converted into kinetic energy without any energy being created or destroyed, well, hey, you're using the law of conservation of energy. All right, should we try one out? So it says to determine the change in energy, so we're looking for the change in energy that an electron would experience in a Van de Graaff generator that has a potential difference, that's just another word for the voltage, of 150,000 volts. So our potential difference is 150,000 volts. Like I said, I'm just going to actually immediately rewrite that as 150,000 joules per coulomb. To me, that tells me a lot more about what that quantity is actually saying, right? It's how many joules of energy something will gain or lose by moving through that potential difference for every coulomb of charge that it has, okay? So we want to determine the change in energy that the electron, hey, we know something about an electron because it's on the back of our formula sheet. Whoops, I'm thinking of the electron's mass. We haven't had to use that yet. 1.60 times 10 to the negative 27 coulombs is the charge of an electron. Again, in case you've forgotten, right, the electron has a charge of minus 1 e, and then e is just the elementary charge, 1.6 times 10 to the negative 19 coulombs, okay? So that's the charge of an electron. Well, hey, look, we're trying to figure out what its change in energy will be. What we have is the potential difference, right? The change in potential energy, or the change in energy it will experience for every coulomb of charge it has. Well, we also know how many coulombs of charge it has, right? So definitely you can tell just from what we know that this is a job for our new equation here, but also just kind of by thinking about it, right? This literally tells us what the change in energy will be if allowed to move between those two places for every coulomb of charge, and we know how many coulombs of charge it has. So we can probably predict that the answer is going to be, we need to take this and multiply it by the number of coulombs of charge, which is exactly what the formula tells us to do, right? We want to find its change in energy. Right now that's being divided by the charge, so multiply both sides by the charge, and sure enough, like we predicted, the change in potential energy will be the charge times, whoops, wrong letter, times the potential difference, right? The change in energy per coulomb of charge. So this checks out. So now putting in our numbers, we get that change in energy will be 1.60 times 10 to the negative 19 coulombs times 150,000 volts, or 150,000 joules per coulomb, right? And look at that, joules per coulomb times coulomb. We're left with joules, the unit of energy. So I got that this electron's change in energy would be 2.40 times 10 to the negative 14 joules. Okay, I know it looks like I rounded that early. I actually didn't. That really is what your calculator gives you. Well, really, your calculator gives you 2.4, but we know that we get 3 significant digits. By the way, you might be saying, why do we get 3 significant digits? The only number we're given is 150,000, which has 6 significant digits. But careful, we did use this, right? And this is a rounded value. The actual charge of the electron has more digits than this, okay, down to our finest measurements. So be careful, right? We use this number, it was given to us, and it still limits the precision of our answer, okay? But there we go. That is the amount of that's the change in energy that would occur. Now this next part asks us how much work would be done on the electron. Well, we just found the electron's change in energy. What is work? Well, work is the change in energy, right? In fact, that is just the work energy theorem. Okay, that the amount of work done on an object is equal to its change in energy, or how much an object's energy changed by is the work that was done on it. So really, this is just applying physics principle number 3, right? The work energy theorem, the simplest equation on your formula sheet. Really not even an equation, more of a definition. Work is the change in energy. So the work done is also 2.40 times 10 to the negative 14 joules. That is how much work the Van de Graaff generator with its electric field did on our electron. Okay, let's try out another one. Alrighty, so electrons are emitted from this electron gun, it's called, okay? Essentially, it's something that causes electrons to fly from here to here. Okay, let's just get a feeling for this situation, read it a bit more here. From rest up to a maximum speed of 85% of c. Now, c is going to be a number you are very, very familiar with by the end of Physics 30. In fact, even when we start Unit C, the next unit, okay? But c is the speed of light in a vacuum, okay? So that is 3 times 10 to the 8 meters per second, or 300,000 kilometers per second, okay? Very fast. In fact, the fastest possible speed in the universe. Nothing can ever go faster than c, 3 times 10 to the 8 meters per second. Anyway, it's a number, it's a speed. We can work with a speed, right? It's just a number. So calculate the electric potential difference. What's that again? What's another word for that? The electric potential difference? The voltage, right? That must be present across the plates. We sometimes call this the accelerating voltage. You can probably put together why, right? That voltage is going to be accelerating charges. The fact that there's a potential difference causes charges to accelerate. They lose that potential energy. It's converted to kinetic. They're accelerating. The same way a gravitational potential energy difference causes things to accelerate towards the Earth or whatever the source of the gravitational field is. Okay, so we want to calculate the voltage that must be present across the plates. Be certain to specify any physics principle used and where you use them. So let's just start out kind of getting our bearings here. I'm going to explain to you a little bit what this apparatus is, but notice here, right, there's a positively charged plate and electrons are flying out of here to here. Does that make sense? Would a negative electron fly towards a positive plate? Yeah, right? Opposites attract. So those negative electrons are feeling a very strong force towards the positive plate. So they're shooting that way. Okay, hence the name electron gun. This is basically shooting electrons from here to here. Now notice it's hooked up to an electrical source, probably honestly just a battery. There's the negative terminal here that's attached to this, the positive terminal here that's attached to this positive plate. Okay, and if we take a look here, right, this actually makes sense. Negatives would want to get away from the negative terminal of the battery and head towards this. We know positives don't move, right? But negatives would then want to get to here. If you were a positive, you would want to move away from the positive terminal to here, right? Really what it is that negatives are pulled out of here. So electrons are essentially pulled out of these plates. Hey, if we pull negatives out of the plates, that's going to make them negative, right? That's going to make them positive. We're taking negatives away. That's why these plates are left positive. So they move through here, through the battery, they get to the negative terminal, and they move that way. A battery, you can almost think of a battery as like a pump for charge. It pumps charge from one place to another, okay? Now, we call this the cathode, and we call this the anode. So the negatively charged plate is the cathode. Now, you chemistry people might be saying, whoa, that's weird. Why would we do that? Because in chemistry, a cation is positive and an anion is negative. Well, the reason we call it a cathode is that a cation, a positive ion, would move towards it, right? Which if you've taken electrochemistry in Chemistry 30, you know is the same idea, right? So it's called the cathode because a cation would go towards it. This is called the anode because an anion, a negative ion, would go towards it. Anyway, all of that honestly is not needed to answer this question, but it is nice background to just kind of understand what we're looking at here. So what do we know? It says that electrons are emitted from this gun from rest. Okay, so we know their initial speed is 0. They start out with a speed of 0 meters per second over here at the cathode, up to a maximum speed of 85% of the speed of light, 85% of c. So the final speed they have over here by the time they get accelerated all the way to the cathode is just 85%, so 0.85 times c. And again, c from the back of your formula sheet is 3 times 10 to the 8 meters per second. Now, we also know that they are electrons that are being fired, so we automatically know their charge, and we actually already know their mass. Okay, we'll see if we need both of those, but we know their charge is 1.6 times 10 to the negative 19 coulombs, and their mass is also given as 9.11 times 10 to the negative 31 kilograms. So just making a list of what we know here, right? And then also, again, what are we required to find? Well, we're asked to find the electric potential difference, the voltage, right? So the voltage is what we're looking for. We know that's in joules per coulomb. Yes, volts, but let's use joules per coulomb here to think about it a bit more. Well, again, what this is describing is how many joules of energy something would gain for every coulomb of charge that it has if allowed to move through that potential difference. I should say how many joules of energy it would gain or lose, right? Depending on what we're looking at. It could be losing potential, gaining kinetic, or gaining kinetic, losing potential. But regardless, it's about a change in energy per coulomb of charge that it has. Well, taking a look at this situation, what's happening here? The electrons have no kinetic energy here. Suddenly they have a lot of kinetic energy over here, right? What's happening is that electric potential energy, these negatives are far from a positive plate, so they have a lot of electric potential energy. That is being converted into kinetic energy, the motion of the electrons, right? The same way a ball that is up very high has a lot of gravitational potential energy, releasing it converts that into kinetic energy. That's what's happening here, except it's not gravity, it's electrical interactions. So, with that in mind, what is the change in energy that's occurring here? Well, it has no kinetic energy here, and it has a lot of kinetic energy here. Do we have what we need to calculate the change in kinetic energy that occurred? We have the electron's mass, we have the speed they started with, and we have the speed they ended up with. And remember, kinetic energy is just 1/2 mv squared, right? So all we need to do to know to calculate an object's kinetic energy is its mass. Well, check, we have the electron's mass, it's on our formula sheet, and its speed. Well, check, they told us the speed it ends up with. And we also know its mass and its speed at the beginning. So we can find its kinetic energy here. We can find its kinetic energy here. Can we find the change in kinetic energy that then occurred? Yes, right? The change in anything is final minus initial, what it ended up with minus what it started. And then we're on our way to start thinking about, okay, so what was the change in energy per coulomb of charge? Because we also know the electron's charge. So I can see a path forward here to finding the voltage. Let's just first, again, we know the voltage is the change in energy per coulomb of charge. We might not be directly told the change in energy, but we can find that. Because in this case, we can figure out the kinetic energy they ended up with and the kinetic energy they started with, right? And that is the change in energy they went through. So the change in energy here will be kinetic energy final minus kinetic energy initial, right? And kinetic energy final, well, again, EK is 1/2 mv squared. So the final kinetic energy will be their final speed squared times their mass divided by 2 or multiplied by 1/2, whatever floats your boat, minus, we kind of know they have no kinetic energy initially, right? Because their initial speed was 0. So we could, if we want, we could say 0 there, or we could write it out mv initial squared over 2, and now say, okay, the initial speed was 0, so that's 0. So the change in energy here is actually just going to be the final energy that they had, right? The final kinetic energy, because they started out with no kinetic energy. So all of that electric potential energy was converted into kinetic energy as they went from here to here. So we find the change in energy here will be mass times their final speed squared over 2. Putting in our numbers, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. The speed they got up to was 85% the speed of light, so 0.85 times 3 times 10 to the 8 meters per second squared. And then dividing that all by 2, I found that the kinetic energy they ended up with, and therefore, since they started from 0, the change in kinetic energy they experienced was 2.96189 times 10 to the negative 14 joules. Okay, now, where did that kinetic energy come from? Because energy can't be created or destroyed, right? It's always conserved. Okay, I mean, kind of what we're applying here is the law of conservation of energy. The kinetic energy came from the fact that there's a difference in the potential energy, right? They had potential energy here. They have less potential energy here. Now, that wasn't destroyed. It simply became kinetic energy. Okay, so in a sense here, what we're applying is physics principle number 5, though you would actually also get away, and sometimes diploma questions do this where they mark, it depends on the question, but often applying one is similar to applying the other, because a change in energy, right, when one type of energy increases, the other decreases. You can look at that as the work energy theorem. The change in energy of an object is the work done on it. But you can also look at it as conservation of energy, right? Because when one type of energy changes, decreases, or increases, another type must decrease or increase because it can't be destroyed. It can just convert from one form to the other. So I'll go with physics principle number 5 as kind of what we're applying here to move to the next step of saying, okay, so what must the voltage have been, right? To allow them to gain this much kinetic energy, what's the potential difference they must have been accelerated through? So again, just to see where we are here, we found the electrons' change in energy. Now we're just interested in what was their change in energy per coulomb of charge, aka the potential difference, the voltage. So moving here now to step 2, let's now find that potential difference. We set it up. We said the potential difference is the change in energy divided by the charge. Well, now we found the change in energy, so every electron gained that much kinetic energy by moving through this voltage, okay? And every electron has this much charge, 1.60 times 10 to the negative 19 coulombs. So the voltage they're in, the difference between those two positions in terms of potential energy for every coulomb of charge can be found by figuring out, all right, well, how much did the electron's energy change by divided by how much charge it has. So when I put that into my calculator, I got that the potential difference between the cathode and the anode, those two positions, must be 185,118.125 joules per coulomb, or to, I guess, 3 significant digits, just based on using this, this, and this, we would say 1.85 times 10 to the power of 1, 2, 3, 4, 5 joules per coulomb, or let's use volts just so we sometimes use that and we're comfortable with it. That's the potential difference. And again, like all voltages, aka potential differences, this is a comparison between two positions, right? It's saying between these two positions, charges will gain or lose that much potential energy for every coulomb of charge that they have, right? How do we know? Well, because we saw some electrons go through it, and we know how much kinetic energy they gained, and we know the charge of the electron. So we can figure out how much they gained per coulomb of charge that they have. All right, so go ahead and try this one out as a starter. I'll give you some other recommendation questions that you can work on as well to take a little, practice break, stop listening to my voice for a little bit and try out some questions on your own. Always good to, while it's fresh in your brain, take some time to master these concepts. But start out with this one, page 565, number 2. You're given a charge that's being moved from one charged plate to an oppositely charged plate. So we're moving it through an electric field. And it tells us that the potential difference between the plates is 500 volts, 500 joules per coulomb, right? And it asks how much electric potential energy will the charge gain. So I'll let you try that one out, okay? And these ones from your formative practice assignment for this lesson are actually all also doable now, okay, as well. So again, take a little break, practice this for a bit, solidify the concepts, right? I know the videos get long because we're covering what we would normally cover in like a 3-hour class per video lesson, right, for a quarter system, okay? So take a break, try these out, and then you can come on back to the video when you're feeling up to it. As always, don't forget the solutions, both my solutions and the textbook solutions are always posted in the agenda for all of those practice questions. Try them out. If you get stuck on any, you can consult the solutions, or you can also, of course, always reach out to me, book a meeting, send an email, whatever it might be. All right. Well, now let's move on here. All right, so in the previous lesson, we introduced and defined the electric field, right? And we talked about how electric fields are defined in terms of the force they would cause a test charge to feel per coulomb of charge that test charge has, right? Newtons per coulomb is the unit of electric field. So if they're in a 10 Newton per coulomb electric field, all that means is that a 1 coulomb charge will feel 10 newtons of force because of that field, right? A 2 coulomb charge will feel 20 newtons of force because of that field. Now, a uniform electric field and a uniform electric field is just one that has the same value at different positions, meaning it's not changing when you look in different places within that field. It's always got the same value of the electric field, okay? Uniform electric fields can also be defined in terms of the potential difference that exists between two positions within that field. It's just another way to quantify how strong an electric field is. If there is a very big difference in potential energy between two positions, that's probably a pretty strong field, right? So just for example, in a stronger electric field, it's going to require more work per coulomb to move a charge from one position to another, right? In other words, its energy will change by a larger amount if you move it from one position to another in a stronger field versus a weaker field. We'll think about this here in a second, but let's just look at the equation because the equation backs that up. The electric field, as long as it's a uniform field, can be defined as well and quantified as the potential difference per unit of distance that you've actually moved within that electric field. Let's just think about this a little bit, what we're saying here. So again, going back to the gravitational field to think about this idea before we apply it to the electric field, okay? What we're saying here is essentially, imagine, two different gravitational fields. You've got Earth, you've got Jupiter. Earth has a lot less mass, and so the gravitational field it generates is a lot weaker. Jupiter has a much larger mass, so it has a much stronger gravitational field at its surface, okay? Now, what we're saying here is if we imagine moving from one position to another in Earth's gravitational field. So that's our change in height. Just to give it a number, let's say it's 1 meter. Versus doing the exact same thing in Jupiter's stronger gravitational field. Let's call that, once again, the same change in distance, just in a stronger field. Okay, now let's think about this. We know there is a change in potential energy associated with that in both situations, right? There's a change in potential energy associated with moving from one position to the other, both on Earth and on Jupiter. Which one, to move 1 meter in Jupiter's gravitational field versus to move 1 meter in Earth's gravitational field, which of those is going to be associated with a larger change in energy? Well, it's going to be Jupiter's, right? I mean, look at the equation. It's a stronger gravitational field. We are going to be fighting stronger gravitational forces to pick a 1 kilogram mass up 1 meter on Jupiter than we would be on Earth, right? The G in this equation is larger. And so all we're saying here is another way to think about how strong a gravitational field is to think about how much more energy an object's energy changes by from moving it a distance in that field versus another field, right? Another way to quantify the strength of a field is to say, how much does an object's energy change by when moving it through a distance within that field? It's essentially just doing this and saying, okay, so one way to think about how strong a field is that if its energy changes by more when you move it through a meter than it would in another field, that field is a stronger gravitational field. Now that is all this equation is talking about, except in an electric field, not a gravitational field, okay? So it's the same idea. It's saying if you were to, right, move some distance from one point to another in this weaker field, let's just once again say it's 1 meter, and do the same in this stronger field, there's going to be a difference in potential energy between those two positions in both fields, right? But the magnitude of that in the weaker field versus the stronger field, there's going to be a bigger change in energy per coulomb of charge you have. In other words, a bigger voltage or potential difference between these two positions in the stronger electric field than in the weaker electric field, right? For a charge to move 1 meter in this field, that's a bigger change in energy than in this field because it's a stronger field. The forces associated with it are larger. You lose more energy or gain more energy by moving around in this strong field than in this weak field. Just like up here in the gravitational field, right? An apple gains more energy by being lifted from here to here on Jupiter than the same change in height on Earth. It's the same idea here. Let's say an electron loses more potential energy by going from here to here than it would from here to here, even if that's the same distance. So that's all that equation is saying. It's saying you can quantify the strength of an electric field by thinking about how big is the change in energy that happens per coulomb of charge for a given change in distance between two positions. And there you go. Okay, now an important note. This equation and this idea of, quantifying the electric field in terms of the voltage for a given distance really only makes sense for uniform electric fields. Again, what is a uniform electric field? To be honest, 90% of the time it's the field between two plates, okay? But what it means, what a uniform electric field means is, well, uniform, unchanging, right? Meaning that if you're here, it is 20 newtons per coulomb. If you're here, the electric field is 20 newtons per coulomb. Here, 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 here. Anywhere inside this electric field, it is 20 newtons per coulomb. So no matter where you are in this electric field, if you're a 1 coulomb charge, you will feel 20 newtons of force. Okay, whether it's up or down depends on whether you're a positive or negative 1 coulomb charge, but that's the idea, right? If you're saying, how could that be possible? Well, think about it. If you're closer to this plate, you're closer to the positive, but you're also further from the negative. So if you're positive, you're more repelled by this, sure, but you're less attracted by the negative because you're further away. If you're down here and you're positive, let's say, you're further away from this, so now you're less repelled by this, but more attracted to this because you're closer to it. So there's this trade-off no matter where you are in the field, okay, that's how we get it to be uniform. Okay, so just a note on what a uniform electric field is first, and why this equation only really makes sense for it and doesn't make sense for a non-uniform electric field, like the one surrounding a point source, for example, okay, is because the electric field strength is changing constantly. Now, I shouldn't say it doesn't make sense, but we don't really have the equations and ways to deal with it because we haven't learned calculus yet, okay? So I'll just, again, this is a non-uniform electric field because, again, we know this would be KQ over R squared, right? But we know that the electric field is, and therefore we know, I should say, that the electric field is much weaker here than it is here. It is not, 20 newtons per coulomb here or here or here or here. The electric field is actually getting weaker as we go further and further away. KQ over R squared, right? So this is a non-uniform electric field. And why this idea doesn't really make sense for this one is that if you think about it, a change in distance, if we think about moving from that position to that position, right? Well, now we're not just changing how far away we are, we're significantly changing the electric field strength itself. So two things are changing as we move from here to here. Not just our position, but also the strength of the electric field, right? And what's more, Out here, it would be even more different, right? So all changes of 1 meter are not created equal in a non-uniform electric field. The difference in voltage from here to here would be very different than the difference in voltage from here to here, right? Essentially, two things, both of these are now changing within the same field for a change in distance of just 1 meter, right? It's not a uniform electric field. And that's why this equation, at least until you learn calculus, doesn't work very well for describing a non-uniform electric field, right? If we're saying the electric field could be defined as the potential difference between two positions and how far apart those two positions are, right? Well, that kind of breaks down if this change in distance of 1 meter would give us a completely different voltage than this change in difference of 1 meter, because the electric potential energy out here is a lot lower than the electric potential energy in here, right? That's not a problem for this uniform electric field. No matter where I am in this uniform electric field, because the electric field has the same strength anywhere, this change in distance of 1 meter will always be associated with the same potential difference. The difference in energy something would have here versus here is actually the exact same difference in energy it would have here versus here, because it is a uniform electric field, okay? Right? Tying it back to the gravitational field once again, okay? You're right, the gravitational field is actually also non-uniform. It also decreases as 1 over r squared as we get further and further away. Near the surface of the planet, it's, it might as well be uniform for this little slice here. We're essentially zoomed so far in that it's pretty much uniform, okay? But if we zoom out, we can see that it's not uniform. And so that would also stop making sense, right? If I'm thinking about this change in height versus this change in height, okay? Again, as I move from here to here, sure, my height is changing, but so is the gravitational field strength along with it, right? Essentially, two things are changing at the same time, making this not a great way to think about it, okay? Until you learn calculus once again. All right, so there is the equation that we can use. Again, this works for uniform electric fields, and it's just another way of quantifying how strong the electric field is. If there's a bigger change in energy for the same distance, right, between the two positions that you've moved, then you're in a stronger electric field. Stronger electric fields are going to require more work per coulomb of charge to move a charge from one position to another. Weaker electric fields will require less work. The energy of the charge will change by less by moving between those two positions. So here is the formula on your formula sheet. Okay, as always, when you get a new formula, good idea to go find it, introduce yourself to it on the formula sheet, but there it is. Let's just introduce ourselves to it a little bit. We know all of this stuff, actually. The delta V, that's the potential difference, or the voltage between the two positions we're comparing in the field. Again, voltage is fundamentally a comparison. What would be the difference in energy of a charge for every coulomb of charge that it has between these two positions, right? Joules per coulomb. E, we know that. E with the little arrow above, that is the vector, the electric field. It's the magnitude of the uniform electric field, because again, this equation really only works well with a uniform electric field. And delta D is the distance between the two positions that is parallel to the electric field. In other words, how far you have to move with or against the field to go from position 1 to 2. And again, that's just because, again, if we move perpendicular to the electric field, have we actually changed our potential energy? Right? Like if I take an electron from here to here, does it have a different amount of potential energy? No, right? Only moving it with or against the electric field can change its potential energy. Same as in gravity. If I take a ball and I move it from here to here, have I changed its gravitational potential energy? No, right? It still has the same amount, still the same mass, still in the same field, and still at the same height. EP equals mgh. So none of those things have changed. The only way to change the ball's potential energy would be to move it parallel to the gravitational field, right? Change its height to actually give it more potential energy or take away some of its potential energy. Just an important note on this that sometimes throws students off, especially since the equations show up at the exact same time and have some of the same variables. Be careful about mixing up the E in this equation for energy with the E in this equation for electric field, right? What's the clue that tells you one is energy and one is electric field? Well, look, this one's got an arrow above it. It's a vector. Is energy a vector? No, but electric field is, right? And look at this one. No arrow above. It's a scalar. Is electric field a scalar? No, electric field has a direction, right? But energy is a scalar. So careful. Don't mix up the E scalar energy with the vector E electric field. All right. All right, so we kind of just covered this, but now it's asking us, when should you usually use the above equation, so this one, and when should you usually use the one below, so this E equals KQ over R squared that we first learned when we started talking about electric fields? Well, as we kind of just got into and saw the reason behind, right, this one works really well in a uniform electric field. It doesn't make very much sense in a non-uniform electric field because, again, as you move through that change in distance, every centimeter or millimeter that you move, the electric field strength is changing as well, right? So it doesn't really make sense there, okay? So like we said, right, use this one for uniform electric fields. It doesn't really work in non-uniform because then our electric field is constantly changing as well as we move through that change in distance, right? To really drive that point home, try rearranging the equation for the voltage, right? How would you calculate the voltage? Because what are you going to put in as the electric field strength, right? As you moved from here to here, the electric field strength changed. So you don't have one electric field strength to put in there to calculate the voltage between these two positions. The electric field strength's constantly changing, right? That's why I say we would need to learn calculus to be able to properly do that. All right. And as for this one, when does this one work? Well, it's kind of reversed, right? This one works really well for a non-uniform electric field, one that changes as you vary the distance, but it doesn't work very well. It doesn't make a lot of sense in most of the uniform electric fields that we see. And to understand the reason why it doesn't work that well for uniform electric fields, honestly, it's because we typically just don't have the information we would need to use it. So to see why, let's just take a look at we kind of already have, but take a look at what typically gives us a uniform electric field. To be honest, most of the time, it is this. It is two charged parallel plates. That's going to give us, in the area in between them, a uniform electric field for reasons we discussed, right? You can move further from the positive plate, but that just means you're getting closer to the negative plate, so that everywhere within here, the field actually stays the same magnitude. So typically, this one is more handy when we're dealing with charged parallel plates. So this situation here. And typically in those, we really don't know what charge is on the plates. And what's more, we also, the separation distance we are from this plate is different from this plate. So we have, again, these are both producing their own electric field. What we see in the middle here is the result of adding the electric field. So this isn't actually one electric field, it's the resulting field in between these two charges that are each producing their own electric field. And that is why this equation doesn't actually work very well, right? The Q, we typically don't know the charge on the plates, and it's also, this is not really one electric field, it's an overall electric field resulting from all of the many point charges on this plate and this plate adding up to give us the overall field in the middle there, right? So what produces non-uniform fields? I mean, it's typically, we've seen, point charges, right? A little positive charge gives off an electric field like this that we know is non-uniform. It changes depending on where you are. If you're closer, it's stronger. If you're farther away, it's weaker, right? So point charges, even multiple point charges, if you had a positive here and a negative here, right? We know the electric field would do something like this, because it's the force that a positive test charge would feel in terms of direction, right? Something like that, okay? That's also a non-uniform electric field. The strength of it is very different here than it would be over here, or here, or here, etc. Okay, so just showing that again here, right? The electric field would be stronger closer to this point source than it would be out here. Stronger here, weaker out here. This equation shows us that, right? It's inversely proportional to the distance squared, okay? Or just to show it with a negative point source charge, right? All that changes is the electric field direction, because again, it's what a positive test charge would feel, and a positive test charge would feel attracted to a negative towards it, right? But again, same idea. Stronger here, weaker out here. Non-uniform electric field. It does change as you move to different positions within it. Now, what about this third equation that we have involving the electric field? What about, this is almost like the definition of the electric field, right? The force felt by a test charge in the field for every coulomb of charge that it has, right? What about this one? How does it work in uniform electric fields versus non-uniform electric fields? Well, again, it's not like any of this is changing the concepts, right? This is the same electric field in this equation and this equation. It's just that knowing these variables and having this set up makes this equation work better for uniform and this equation work better for non-uniform. If you had all of the information, don't get me wrong, both would give you the same electric field as a result because it is the same electric field concept that we're talking about there, right? And same goes for this one. Now, in a uniform versus non-uniform electric field, does anything here that we're talking about change, right? It really doesn't. We're still talking, the electric field still represents the force that a test charge would feel for every coulomb of charge that it has. So, taking that over to our diagrams here, if I want to think about the electric field at, let's say, this location, right? What I'm thinking about is how big would the force, the electric force, that a positive test charge would feel for every coulomb of charge that it has if placed there, right? So if I know the force that it feels and I know its charge, I can calculate the strength of the electric field there, okay? And same goes for this, right? If I think about, okay, what's the electric field like here at this location in this non-uniform electric field? Well, I'm still thinking about at that location, sure, it might be a different force down here, but we're not talking about down there. We're talking about at this location. If I can think about the electric force, that a positive 1 coulomb test charge would feel there, or if I know that maybe if I know that force, right, and I know how many coulombs of charge this test charge has, I can figure out what the electric field strength is there. Right? So this works for both. This works for uniform, non-uniform, because all it's talking about is what force did a test charge feel when placed in that field for every coulomb of charge that it had? How many newtons per coulomb? That doesn't change if we're in a uniform versus non-uniform field, right? We're still talking about the same idea. If you put a test charge at that location, how many newtons of force would it feel per coulomb of charge that it has? Okay, so just kind of summarizing that here, right? We can use this in a uniform and a non-uniform. This is really just using the definition of the electric field. If you know the charge of a test charge and you know the electric force that it felt at a given location, you can use those to determine the electric field strength at that location, right? Doesn't matter if the electric field would or would not be different at another location, right? A non-uniform versus a uniform. We're looking at that location and the force that a charge felt there for every coulomb of charge it has. That's just the definition of the electric field at that location. All right, let's talk about everyone's favorite, some graphing. How could we graph these relationships? So it wants us to sketch a graph. Now, when we're sketching a graph, always the same principles at work, right? Always the same thought process. What are our variables? What goes on the y-axis? What goes on the x-axis? And then what equation tells us how that graph should look, right? What equation tells us when x changes like this, y should change like that, right? That's it. It's not guessing. It's not making it up. Let the equation tell you. So sketch a graph of potential difference. What's that another name for? That is another name for the voltage, right? In fact, a better name for the voltage, if you ask me, okay? As a function of distance, okay? So distance, we know if we're thinking voltages, we're thinking about the difference between two positions, right? The change in distance in a uniform electric field. So we would be thinking about, this equation anyway. But look what they told us here, right? We're interested in the relationship between voltage, potential difference, and distance, okay? So now we go to our formula sheet and we think, all right, what equation relates these, right? What equation relates these? Well, there's only this one that contains the voltage and the difference in the distance between those two positions, right? So I'm thinking this equation right off of the bat. So let's write that down. All right, so we're sketching this graph. We're trying to graphically represent this relationship. Now, always the same thought process, right? We got to now decide what goes on our y-axis and what goes on our x-axis. They were kind of nice here. They told us potential difference as a function of distance. So that kind of gives it away. Remember, it's always y as a function of x, right? Responding as a function of manipulated. But even if they hadn't given us that clue here, we probably could have figured it out because we know the responding or dependent variable, the one that depends on the other one, should go on our y-axis, right? And the manipulated or the independent variable, the one that when you change it, as a result, you see a change in this one, right? That should always go on the x-axis. Okay? And if we think about these two variables, we can kind of arrive at that ourselves, right? What makes more sense? That you change the distance you're moving in a uniform electric field, and as a result, you get a different voltage, right? So like that change in distance versus that change in distance. Does it make more sense to say we could manipulate how far we're thinking about, and as a result, there would be a different difference in potential energy for this change in distance versus that one? Or would it make more sense to say we could change the amount of potential energy and as a result, we would have moved a different distance, right? You can kind of see there like the cause versus effect. It's more easy to manipulate the distance, right? That feels more natural. We could think about going this far in the field versus this far in the field. And as a result of that, we would have a different change in potential energy between these two positions versus these two positions, right? It almost feels a little bit backwards to say we would change the amount of difference in potential energy, and as a result, we would have moved through a different distance, right? That almost gets the like cause and effect backwards. See what I mean? So it does definitely feel like this is our responding variable and this is our manipulated. But like I said, they gave it away anyway by saying as a function of, because it's always y as a function of x. So that means the potential difference, the voltage, goes there on the y-axis, and the change in distance goes there on the x-axis. Okay, so there we go. We've got ourselves set up. We've started sketching our graph. And now, like always, right, again, let the equation tell you how this graph looks, right? It's often helpful to solve the equation for what's on the y-axis, because that way then you can just say, okay, so what happens to that variable as our x variable changes? So let's solve this for the voltage, multiply both sides by the distance. And now we can kind of easily see, right? We can say, okay, so what happens when x, the distance, is very small or even 0, right? Well, the equation shows us if this were 0, then this equation is just doesn't matter times 0, right? So we can see here, all right, when this is 0, when x is 0, y will also be 0. So our graph starts here at the origin. And then we just ask ourselves, okay, then what happens as x gets larger, right? As this distance gets larger, what's going to be happening to the voltage? Well, as I make this larger, I'm multiplying by a larger number over here. What happens to my answer? It also gets larger, right? As the distance increases, the voltage is also increasing. So we know we're headed up this way. The only question left is what kind of shape are we headed up in, right? Is it curved? Is it straight? And once again, we don't have to guess. The equation shows us. And so looking at the equation here, right, we can use it to think about that. So if I were to double the distance, what would happen to the voltage, right? What would happen to my answer? If this number were 2 times larger, well, I'd just get a voltage that was also 2 times larger, right? That distance isn't being squared or square rooted or cubed or inverse or anything funny like that, right? It really is just the electric field times the distance. So if the distance is 3 times bigger, the voltage will be 3 times larger. In other words, whatever factor I increase the distance by, the voltage gets increased by the same factor. Same goes for decreases, right? So we could say that the voltage is directly proportional to the distance, and it's linearly proportional. So when this increases by the same factor. Whenever we run on the x-axis, we will always rise by the same amount on the y-axis. Now, it doesn't mean the run and the rise will always be the same. It just means that for a given run, the rise that goes with that will always be the same, right? If it runs 1, it will always rise 2, for example. Like let's just draw in our line, and then we can think about that, right? What I mean is that if this is 2 and this is 1, let's say, then if this is 2, this will also be 1. For a constant change in the displacement, or the distance, we get the same change in the voltage. Okay, that's what a linear relationship is all about. All right, so next up here, it asks us to state the significance of the slope of this graph, right? Well, the slope is always the same thing, rise over run, right? The y over the x. So looking at our graph, right, what would a rise over a run on this graph, what physical quantity would that represent? And again, we're not guessing here, we're going to let the equations tell us. So is there any equation that has us taking a voltage and dividing it by a distance? And if unsure, we can always go check our formula sheet, right? And sure enough, this would just represent the electric field. So our slope, rise over run, is just the voltage over the distance, which we know is the electric field. So the electric field would be the slope of this graph. If we found the slope of this thing, we'd be finding the electric field that our charge was in, or that at least we're thinking about a charge in for this situation. Looking at it this way as well, we could get the same result, right? If I rewrite it in y equals mx, right? Y variable, x variable, we can see that the slope, m, would be the electric field strength. So just to think about the type of experiment that might give us this graph, right? You can imagine having a uniform electric field, and you're varying the distance between the 2 points you're testing. So you're checking what is the potential difference between maybe those 2 points, and then make the distance slightly larger. What's the potential difference between those 2 points, right? That gives you a new voltage. So you're varying how far apart the 2 points you're testing are, and then recording the voltage between those 2 points over and over again. And if you plot that data on the graph, it might look something like that, right? When the 2 points were this far apart, the voltage was about that large. When the 2 points were this far apart, the voltage was about that large. And then in doing that, if you were to then find the slope of the graph you've created, you know that you would be finding the strength of this electric field that we are in. And thinking about it in that context also kind of supports our idea that it should be a direct relationship, right? If we're thinking about the potential difference per coulomb of charge between two positions, i.e. the voltage, we would expect there to be a bigger difference in potential energy for a larger distance, right? The difference in potential energy between this position and that position, we would expect that to be bigger than between this position and that position. So this checks out. Bigger difference in distance between the two positions should result in a larger difference in potential energy per coulomb of charge to move through those distances. All right, so let's move on to this one here when we can actually maybe try this equation out. It says calculate the strength and direction of the electric field. Okay, well, let's start with direction. We can think about the direction right away. We've got a positively charged plate and a negatively charged plate. Question, how do we define the direction of the electric field? Right, we ask ourselves, in which direction would a positive test charge feel a force if placed into that field, right? So if we put a positive test charge in here somewhere, which way would the positive feel a force? towards the top of the page, right? Up towards this negative plate. It would be attracted to the negative, and at the same time, it'd be repelled by the positive. Either way, that's a force upward. So our electric field in these plates is going to look something like this, right? Okay, and it's everywhere in here, so visually we can represent it like that. But the direction would be towards the top of the page, from the positive plate to the negative plate. Now, to actually calculate the strength, question for you, should I use this? Which one makes more sense here? Or should I use this, right? Well, ask yourself, what's producing the electric field that we're interested in here? It's the plates, right? The plates are producing this electric field. Okay, now we know the voltage across the plates. We don't know their charge. Like, we have no idea what the charge is on this plate. This is like, it's got billions of charges on here that are giving the plate a net charge, right? But we do know the separation distance across the plates. It's 1 millimeter. We know the potential difference, aka the voltage across the plates. Okay, so this seems like a good fit. Plus, it's a uniform field. This equation works really well for a uniform field. Remember, between charged parallel plates, a uniform electric field is produced. Again, because of that idea we were talking about, right? As you move further away from the positive, sure, the positive has a weaker electric field up here, but to make up for that, then you're getting closer to the negative. So its electric field gets stronger, and the effect is that everywhere the electric field is uniform, constant. It has the same value everywhere. All right, so let's go ahead and use this equation. It's already manipulated for what we want. We want the electric field strength, so we just need to plug in our numbers. The voltage across the plates is 1,000 volts. And the distance separating the plates, if we were to go from this position to this position, we know our potential energy would change by 1,000 joules per coulomb, okay? And we would have moved through a distance of 1 millimeter. So 1 times 10 to the negative 3 meters, or 0.001 meters, right? Converting our millimeters to meters. And we get that the electric field strength between these plates must be 1 million. And this is actually a unit that is sometimes used for electric field, so you'll see this used sometime, volts per meter. We could, of course, also say newtons per coulomb. We know that measures electric field strength as well, okay? But volts per meter is often used, and again, that just goes back to the idea you can talk about how strong an electric field is by thinking about the potential difference per coulomb of charge for moving a set distance between them, right? So volts per meter, okay, that you're moving between. All right, so to 3 significant digits, this would be 1.00 times 10 to the 6 volts per meter, or newtons per coulomb. That is the strength of our electric field. All right, now this next one's kind of interesting. It says, repeat at the midway point. Well, okay, we know theoretically, we know that the electric field, this is a uniform electric field, right? So we should get the same answer. But how do we mathematically come up with that? How can we show that, yes, we do get the same answer? Well, let's think about this, right? If we take a charge and we move it from here to here, all the way across the plates, we know that we're changing its potential energy, right? Same way if I lift an apple in a gravitational field from here to here, I change its potential energy, okay? And so if I only lift it halfway, do I change its potential energy by the same amount, right? Again, if we were in a gravitational field and I lift something from here to here versus only lifting it from here to half as high, right? How will the change in potential energies compare between those two situations? Well, I'll give it half as much potential energy, right? This is associated with this change in potential energy. So if I only lift it to half the height, I'm only going to give it half as much potential energy, right? Or take away if I'm moving in the other direction. So it's the same idea here. If there are 1,000 joules per coulomb of potential energy to be changed by going from here to here, well, halfway across, there would only be 500 joules per coulomb, right? Going halfway across is going to result in the potential energy changing by half as much per coulomb of charge. In other words, the voltage at the halfway point is going to be 500 volts instead of 1,000 volts. Okay, so again, just if the potential difference from here all the way across is 1,000 joules per coulomb, then from here halfway across, it'll just be 500 joules per coulomb. Half the distance means half the change in potential energy happening. And of course, the distance is also in half, right? If I think about going from here to here instead of all the way across, that's only a change in difference of half of a millimeter, or 0.0005 meters. And so we can see, right? Look at this equation. Look what's about to happen. Yes, our numerator is half as large, but so is our denominator, right? So we should be about to get the same answer. And sure enough, 500 volts over 0.005 meters also gives us 1,000,000 volts per meter, or newtons per coulomb. They're both units of electric field. Okay, so like we would have predicted, because this is a uniform electric field, right? Parallel plates create a uniform electric field. We still get the same result. It's still the same electric field. It's not a different electric field. We're not talking about a new question now, right? So it's a good sign that we got the same answer as we did in A. Okay, now C asks us to calculate the maximum change in speed of the proton. Well, all right, we've got a proton in this electric field. We know a proton is charged, so it will feel a force when it's in an electric field. We know that force will accelerate it up to the top plate, right? And that's why its change in speed is even happening. It's going to be starting down here, and it's going to get faster and faster and faster, and then crash into this negative plate. So how can we figure it out based on the information we have? Well, it's a proton, so automatically what do we know? We know its charge and its mass, right? Those are both on the back of our formula sheet. Proton has a charge of positive 1e, e being the elementary charge, which is 1.6 times 10 to the negative 19 coulombs, right? And the proton has a mass of 1.67 times 10 to the negative 27 kilograms. All right. Now let's think about this. We also know the potential difference across the plates, right? In other words, we know how much a charge's energy would change by for every coulomb of charge that it has by going from here to here, right? By moving from this position to this position. That's what this number represents. The number of joules of energy exchange it could go through by moving from this position to this position. Well, that's actually exactly what's happening to our proton, right? It's going from here to there, and as a result, an energy change is happening. We can even see here, this has a positive charge. It's near the positive plate, so it really wants to go that way. Just like how a ball being held above the earth really wants to fall downwards, this really wants to accelerate upwards, right? It has a lot of electric potential energy here. As it moves this way, it's going to be losing that electric potential energy. But is that electric potential energy just disappearing? Is it being destroyed? No, right? We know that energy is never created or destroyed. So what's happening to it? It's losing potential energy, but gaining kinetic energy, because it's going to go faster and faster and faster until it collides with that negative plate. So really what we have here is just kind of a case of conservation of energy, right? This is, we could say it's physics principle number 5. We know that potential energy is being converted into kinetic energy. It has a lot of potential energy here. That's all going to get converted into kinetic energy as it moves from there to hit the plate. And it's physics principle number 5 that tells us this. The change in potential energy will just have to be the same size as the change in kinetic energy, right? Yes, one is being gained and the other is this one's being gained while this one's being lost. But however much potential energy is lost has to be equal to the amount of kinetic energy being gained. Now, how does this help us? Well, if we can figure out how much its kinetic energy changed by, and kinetic energy is just mass times speed squared over 2, we could use that to figure out the proton's change in speed, right? If we figure out how much its kinetic energy changed by, well, the mass didn't change, so we can use that to figure out how much its speed changed by. Worth mentioning, by the way, this is actually not the only way to approach this question, because we've also found the electric field. We could use that to figure out the force on the proton, and since we have the proton's mass, with a force and a mass, we can find acceleration with Newton's second law, right? And then we could actually just use our kinematics equations and figure out, all right, if we know its initial speed, we know its acceleration now, we know the distance it's going to travel, could we figure out its final speed and then use that to figure out the change in speed? So in that case, we'd be using probably this one, right? We want the final speed so we can figure out the change in speed. The initial speed appears to be 0. We could figure out the acceleration, like I said, with the electric field. We could get the force, and with the force and the mass, we could get the acceleration. So we could get the acceleration, and we know the distance it's traveling through. It's just traveling across the plates. So that's an alternate way to do it. But to kind of treat it, take these new ideas and apply them here with the change in energy. Plus, I think it's honestly easier to approach this from an energy standpoint in this case. Let's try using this change in energy idea here. Okay, so just a reminder again here, right? We know that we have this relationship. The voltage is just the change in energy the charge would experience per coulomb of charge that it has. And so since we're given the voltage, this is how much the proton's energy will change by per coulomb of charge that it has. Well, we know how many coulombs of charge it has. So let's use that to figure out how much the proton's energy will change by. Okay, so the potential difference is just the change in energy per unit charge, right? And therefore, the change in energy is just the voltage times the charge, right? Again, makes sense. This is how many joules its potential energy will change by from moving between the two positions per coulomb of charge that it has. So multiply it by the number of coulombs of charge that it has, and you get the actual change in energy by moving between those two positions. So putting in our numbers, the voltage is 1,000 volts or joules per coulomb, and the proton has 1.6 times 10 to the negative 19 coulombs of charge. So its change in energy will be 1.6 times 10 to the negative 16 joules. Now, what is that change? Well, like we said, it's from potential into kinetic, right? So this is the change in kinetic energy, which we can use to find how much its speed must have changed by, right? Its mass isn't changing, and the only other ingredient in kinetic energy is speed. So again, what we're really applying here is physics principle number 5. Energy can change from one form to another, but it can't be destroyed, okay? So now we know that this change in energy is its change in kinetic energy, right? This change in energy is the change in kinetic energy. And since kinetic energy is just 1/2 mv squared, right? Final kinetic energy is mv final squared over 2. Initial is mv initial squared over 2. And so do you see how this is getting us closer to finding the change in speed? Okay, now, something to talk about here. The maximum change in speed of the proton. I mean, the diagram and everything we've been given kind of leads us to the idea that the proton is at rest anyway. But the fact that they said the maximum change in speed actually even further confirms that it has to have started from rest. And I know it's not immediately obvious why, okay, but it comes down to the fact that we're squaring these, right? Now, mass over 2 would be staying the same anyway here, so focus in on the speed squared final minus the speed squared initial, okay? If you think about going from a speed of, say, like 0 meters per second to 3 meters per second, versus going from a speed of, I don't know, how about even just 1 meter per second to 4 meters per second. Now, both of those are a change in speed of 3 meters per second. So you might think that would result in the same change in kinetic energy, right? But don't forget, this is not a linear relationship. Kinetic energy is directly proportional to the square of speed. So it's actually not, right? The change down here versus the same change up here, it requires much more energy to go from here to this speed than it does to go from this speed to this speed, even if it's the same change in speed. So like here, right? 0 to 3 is a change in speed of 3 meters per second. But if we were to put it into the kinetic energy formula to find out how much kinetic energy that would require, right, we would do something like 3 squared minus 0 squared to get 9, right? But if we were to do it for this one, even though it's the same change in speed of 3 meters per second, 4 squared minus 1 squared, well, that's 16 minus 1, which is 15. So even though the change in speed was 3 meters per second in both cases, the amount of kinetic energy required to do that is much more to go from 1 meter per second to 4 than to go from 0 meters per second to 3. So the maximum change in speed, since we're locked in on this is how much the proton's energy changed by, it actually tells us that, okay, for that amount of energy, the most like bang for your buck in terms of the change in speed can only happen if we're going from starting from 0. That's where we get the maximum change in speed. Otherwise, this change in energy wouldn't be capable of causing as big of a change in speed, right? We can see that for larger numbers, larger changes in speed where VI was not 0, that requires more energy, which we don't have. So all of that confirms what the diagram kind of already suggested, but our initial speed here is 0. So that means the change in kinetic energy that it goes through is just going to be the final kinetic energy it ends up with, since it's starting from 0, right? So to find the final speed, now we can just rearrange this equation. We know the change in energy it goes through, and we know the mass of a proton. The only thing we don't have is that final speed. So let's solve for it. We'll multiply both sides by 2 and divide by the mass. And then if we just square root both sides, we will have solved for the final speed of this proton. Okay, so like I said, we've got all our numbers. Let's put them in and calculate. Here we go. So this proton's final speed will be 2 times its change in energy, which we figured out with the voltage and the distance would be, the voltage and the charge would be 1.6 times 10 to the negative 16 joules. Then the mass of the proton we know from the back of our formula sheet is 1.67 times 10 to the negative 27 kilograms. So putting that into our equation here and calculating, I got that the final speed of this proton would be 437,741 meters per second. Now, I need to be careful here because we weren't trying to find the final speed. We were trying to find the change in speed, right? Now, in this case, because it started from an initial speed of 0, those end up being the same number, but just be careful, right? In some questions, the charge might already be moving. It would be the exact same process, it's just that the initial speed wouldn't be 0, right? You'd have to put in the initial speed there, okay? So our change in speed is V final minus V initial, but again, since we're looking for the maximum possible change in speed, that means we must be starting from a initial speed of 0. And therefore our change in speed to, how many sig digs here again? 3 significant digits would be 4.38, right? Round that 7 up because it's followed by a 7. 4.38 times 10 to the power of 5 meters per second. And there we go. That's the maximum change in speed that could occur for this proton. All right. E asks us to calculate the time taken to pass between the plates if the proton was initially at rest. Okay, so now this one's really confirming that VI is 0 meters per second. Now, we've also just figured out that it ends up with this speed, right? We know V final is 437,741,000 meters per second. Okay, so let's just think about everything we know here. It starts at 0. We know its speed here. We're interested in the time it would take to cross. Okay, now be careful. This is not uniform motion. A common student mistake here would be to forget physics 20 and use this equation. Remember, that only makes sense if it's moving at the same speed the whole time, right? That's definitely not what's happening here. It starts out at a speed of 0. It only reaches that final speed at the very end, okay? In between, it has many different speeds. But we do know, it is true that we know how far it has to go, right? It has to travel a distance of 1 millimeter to get across the plates. So the distance here is 1 millimeter or 0.001 meters. And so pausing there for a second, I noticed that we've got 3 of the kinematics variables and we want to know a 4th. right? So if you recall, right, from physics 20, whenever we have three of the five kinematics variables, the other one being the acceleration, which we actually could find here because we could use the electric field to, again, find the force and then use the mass with the force to find the acceleration. That's another approach we could take, okay? I'll stick with the ones that we already have found, though, right? Recall that if we have three of the five kinematics variables and we want to find a fourth, there is always a kinematics equation for that. There's 5 kinematics equations. Each of them are set up for when you don't know one of the variables. In this case, we don't know the acceleration. Again, we could find the acceleration. It's totally possible, but we've already got the other stuff, so why bother, right? This one is for when, like if you've got acceleration or final velocity or initial velocity or time, and you want to know one of those, right? If you have 3 of those things and you want to know one, this equation will tell you. This is for displacement, initial velocity, acceleration, and time, right? Again, we don't know acceleration, so we probably won't use that one. This one, displacement, final velocity, acceleration, okay, so probably not this one. This one, displacement, we know that. We know the distance it has to move through, right? We know its final velocity. We know its initial velocity. And we want to know the time. So this is just actually a physics 20 question, right? We're back in physics 20. We have 3 of those and we want the 4th one. Totally solvable equation, okay? So this, again, just a reminder, this kinematic stuff doesn't go away. These are fundamental descriptions of how things move. And things are still moving in physics 30. It's just that now it's things like protons in an electric field instead of a ball being kicked off of a cliff or something like it was in physics 20, okay? So looking at our formula sheet, I think that this equation will give us what we need here, right? We've got all this stuff listed out, and we want to find this thing. All right, so let's solve it for time. Well, what's happening to time? It's being multiplied by this whole thing, right? So we could just divide both sides by this whole thing. We could show it like this, but to make things a little, neater and prettier, I might say dividing by this fraction is the same as multiplying by its reciprocal, right? We're dividing by 2, so if I multiply by 2, that will cancel out, and divide by VI plus VF, that will cancel out. And then if I do that to the other side, 2 over VI plus VF, right? If I multiply those two out, I get that the time will be 2 times the distance over the initial velocity plus the final velocity. And here we go. We can just plug in and solve for the time. So the time will be 2 times the distance it has to travel, which is 0.001 meters or 1 millimeter. The initial velocity they told us was 0, and the final velocity we calculated in the previous question to be 741 meters per second. Of course, using our unrounded answer there, right? We don't want to round too many times and end up with our final answer actually being off. So yes, appropriate sig digs when stating our final answer to this question, but then we'll use our unrounded answer when we need to use that number again in the next part. So putting that into my calculator, I got that the time it would take is 4.56891 times 10 to the negative 9 seconds. So a very short amount of time, right? About 5 nanoseconds. But that's not too surprising when we're realizing the strong forces involved here for a tiny mass, right? The proton has a tiny mass, 1.67 times 10 to the negative 27 kilograms. It's feeling a pretty strong force in this, fairly strong electric field, 1,000,000 newtons per coulomb, okay? So it's going to get accelerating very fast. In fact, we found its final speed is about 400,000 meters per second, so 400 kilometers each second, right? So not surprising that it takes a very short amount of time to travel just 1 millimeter, right? It's traveling 1 millimeter in, again, about 5 nanoseconds. So to 3 significant digits, this would be 4.57 times 10 to the negative 9 seconds, or if you prefer, you could say 4.57 nanoseconds, right? Because again, we know that nano means times 10 to the negative 9, means 1/1,000,000th. So this is 5 1/1,000,000ths roughly of a second. All right. So take a little practice break here, okay? Try out this new equation where we use the voltage and the distance to calculate the electric field, or at least use that equation. Might not always be calculating the electric field with it, might be getting the voltage or the distance. Okay, so try this one out, and you can also try out this one, the one that comes right after it, page 568, number 2. Go ahead, give them a shot, take a break from my voice, and then we'll finish up here with just kind of thinking about this voltage a little bit more and moving between positions in an electric field. All right, so in all of the problems that are coming up, I want you to notice that really it's Physics 20 concepts and Physics 20 skills that are really guiding the thinking still, right? I always tell my Physics 20 students that honestly, you're learning most of the stuff now in Physics 20. It's just that in Physics 30, you'll apply it in new contexts, right? Instead of a gravitational field and gravitational potential energy, for example, we're now looking at an electric field and electric potential energy. But all the ideas of changes in energy and work and all that was covered in Physics 20, right? It's just now because of electrical charge and electrical interactions that there's changes in energy going on. So let's try this one out. So a potential difference, what's another word for that again? Voltage, right, of 50 volts exists between two parallel plates. An object with a charge of 2 millicoulombs is placed between the two plates as shown below. All right, so we've got our two plates, and this charge we're being told is 2 millicoulombs. Now we're told that there's a potential difference of 50 volts between the two plates. And again, literally all that means is that if you were to take a charge from here to here, you would change its potential energy by 50 joules for every coulomb of charge that it has, right? So 50 joules per coulomb is the voltage across the entire plates. Okay. Now we're being asked to calculate the work an external force would have to do in order to move the charge to position U. So there is position U right there. All right, so this is an interesting one because what part of moving it from here to here is actually changing its energy? Because remember, the work done is just how much we change its energy by, right? Work is the change in energy. So we're moving it from here to here. And I do think its potential energy will change, right? Definitely. It's here. By moving it to there, we're going to give it, it's positive, so we're going to give it more potential energy, right? Moving it closer to this plate means that if we let it go, it's going to get even more kinetic energy if we were to release it from U than if we were to release it from this position. And so we know that the voltage, again, is equal to how much its energy changed by, aka the work we've done on it in this case, divided by its charge. And therefore, the work, or the change in energy, is just the charge multiplied by the voltage, right? Just multiplying both sides of this by the charge. Now, the question is, we know the charge. We were told the charge on this thing is 2 millicoulombs. That's no problem there. What's the potential difference, though, between this position and this position? We know that it's 50 joules per coulomb across the entire plates, right? To go from here to here, you would change its energy by 50 joules for every coulomb of charge that it has. But what about to go from here to here? Okay, now there's a couple things to unpack there. First of all, okay, is the 5 centimeter distance, is that the distance we need to be thinking about here? Because what I mean by that is, in moving it 5 centimeters, we were partially moving it up, right? And we were partially moving it towards the positive plate. Now, did both of those components of its motion, did both of them change the charge's potential energy, right? Did doing this do anything to change the amount of energy this positive charge has? Does it have any more potential energy here than it does here? When in doubt, let's reference back to the gravitational field, right? If I have a ball here and I move that ball to here, have I changed its gravitational potential energy? Have I changed its height? Right? I can't change its mass or the gravitational field of the Earth, so the only way to give it potential energy would be to move it higher or lower, right? So no, I have actually not changed the ball's energy at all by moving it from here to here. I've done zero work on the ball. I have not changed its height at all, and so I have not changed its energy at all. So going back to this one, we did change its energy, but not because we moved it 5 centimeters on a diagonal. It's actually just because of however far we moved it this way, right? Moving it closer to the plate gave it more potential energy. Moving it parallel to the plate up this way did nothing to change its energy. So really, it's only the fact that we moved it from here to here that changed its energy. So we moved it through, let's think about this. The entire distance across the plates is 15 centimeters. We moved it through 3 of those 15 centimeters. So the change in distance is 3 out of 15, or 1/5 of the total distance, right? Now, what does that mean for the potential difference between these two positions? This is a uniform field. So if we only move through 1/5 as much of the distance between these two positions, right? Well, that means we only move through 1/5 the potential difference. If we lift the ball to only 1/5 the height, right, here to here versus here to here, we would expect this to get 1/5 as much potential energy change as this one, right? So same idea here. So it's moved through a distance of 1/5 the total distance across the plates, and therefore the potential difference here will be 1/5 of 50. In other words, it will be only 10 joules per coulomb, right? Again, that kind of checks out. If it would gain or lose 50 joules of energy for every coulomb of charge that it has by going from here to here, well, to go 1/5 of the distance, it should only gain or lose 10 joules per coulomb, 1/5 as much potential energy. And so there we go. We now know the charge and we know the potential difference that it's been moved through. So we can figure out how much its energy will change by, and therefore how much work will be done on it. So plugging in our numbers, 2 millicoulombs, and milli means times 10 to the negative 3. Again, that's on the back of your formula sheet if you ever forget. Times the voltage, which we've now confirmed is 10 joules per coulomb. And sure enough, right, coulombs over coulombs, we're finding a change in energy, so that makes sense. We get that it would be 20 times 10 to the negative 3 joules, right? 2 times 10 is 20 times 10 to the negative 3, or we could just say 0.020 joules. So that's its change in energy, and since work is equal to its change in energy, we were asked to find the work done on it. So to 2 significant digits, which is what we get here, we could say 0.020 joules. That was the work done on the charge to move it from this position to this position. All right, so now B asks us to compare the amount of work done to move the charge to position U to the amount of work that would need to be done to move it to position R. Well, how much work, the only difference between U and R is in this axis, right? So moving it to position R is actually going to be changing its energy by the same amount as moving it to position U, right? It's the same. The component of the movement that we do that's parallel to the plates does nothing to give or take away its energy. Only moving it this way does. And since U and R are in the same location horizontally speaking, it's going to take the exact same amount of energy, the exact same amount of work will need to be done to move it to R as to U. So it's the same. Right? Going back to the gravitational field, if we think about moving a ball from here to here versus from here to here, right? Moving it that way versus moving it that way, well, either way, they ended up at the same height. They started at the same height, they went through the same change in height, right? And therefore, their change in potential energy and the work required would be the same in both cases. Moving it parallel to the ground here, or perpendicular to the gravitational field, does nothing to change its energy. Okay, so just summarizing it there, right? Moving it parallel to the plates does nothing to change the charge's energy. Only moving it closer or further to the plates, right? In other words, moving it like with or against the electric field can change its energy, but not moving it parallel to the plates. The same way you studied in Physics 20 with gravity, right? Moving it higher or lower can change its potential energy, but moving it side to side, well, that's not changing its potential energy, right? Only moving it like with the gravitational field or against the gravitational field can actually change its potential energy. And therefore, only doing that requires work. All right. So this one, with that in mind, this one's asking us now, which positions would require no work from an external force? In other words, a force that isn't just like if we just let this happen, how it would happen, right? In other words, not the electric force from the plates. Because you can tell if we just let this go, this charge, it's positive, it's going to fly towards that negative plate, right? So which positions would require no work from an external force to move the charge to? And why? Okay, so external force. Let's just, imagine it's our hand. Which of these positions would we have to reach in with our hand here and do work to move it to? Okay, and therefore to change its energy, right? Well, definitely it's a positive charge. So we would need to reach our hand in and we would actually need to apply a force and do work to move it to R, right? We would also need to do work to move it to U. That's very similar to what we were just talking about up here, okay? Now, to move it to T, are we actually like fighting the electric field to do that, right? Would we be giving it any more potential energy by moving it to T? I don't think so, right? It doesn't have any more potential energy at T than it does where it is now, okay? So I think T should be on the list, and the reason is what we were talking about up here. Okay, so for all the same reasons we talked about in this question, T would require no work to move it to, right? It has no more energy there than it does where it is now. Now, would we need to do work to move the charge to S? Or could we just kind of let what's going to happen, right? We wouldn't need to do any work. An external force would not need to do any work to move it to S. A force would do work on the charge because it would change its potential energy into kinetic, but it doesn't need to be an external force. We would not need to put our hand in there and push it over here, right? Again, acknowledging that these charges are too small probably for us to reach our hands in and touch, but just for a visual, right? We don't need to push it to S. The electric force is going to do the work to move it to S. So I would say S should also be on the list, but kind of for a different reason. Not because its energy doesn't change by moving from here to S, but just because an external force doesn't need to act. The electric force will actually do the work of converting potential into kinetic in that case. All right, so just summarizing that there, right? S, not because its energy wouldn't change by going from here to there, but because the question was very specific about no work from an external force. No external influence is required to move the positive charge to there. The electric force will do the work here, changing that potential into kinetic, right? And again, just that connection of, yes, work is the change in energy, but work is also a force acting on a charge over some distance, right? Applying a force for some distance causes a change in energy. It causes work to be done. Okay, and you might remember from Physics 20, this connects back into what we've been talking about. It's really the amount of force that was parallel to the displacement it moved through, right? And that connects back in here, because if we were to move it to here, the only part of the force that we're pushing on it with that's actually doing work, that's actually changing the energy, is the part that's parallel to this displacement. So if that were the angle we were applying the force at, like that, okay, again, only this part is doing the work to move it to a place where it has more energy. This part is doing nothing. And that's why the cosine of theta pops up. Because if we took this force and multiplied it by the cosine of theta, we'd just be finding this component of it. The component that's actually working to move it this way and change its energy. The component that's moving it that way is not changing its energy and not doing any work. All right, and last example here for lesson 2. It's asking us to determine the change in potential energy for each of these cases. State whether it's an increase, decrease, or no change, and state our reasoning. Okay, so an alpha particle moves from C to E. Now, I realize your first question is probably, what on earth is an alpha particle? Okay, we will actually study alpha particles extensively in Unit D, but for now, you can see they are on the back of your formula sheet, right? It turns out they're actually just a helium nucleus, but we didn't know that when we first discovered them, and the name alpha particle has stuck. More on that in Unit D, okay? But the alpha particle, you can see its charge is positive 2e. And hey, what's E? E is 1.6 times 10 to the negative 19 coulombs. So the charge of an alpha particle is just double that, and positive. So in other words, it's positive 3.2 times 10 to the negative 19 coulombs. Okay, now we're going to take that positive alpha particle, just draw it as a positive, and we're going to move it from C to E. Okay. Now, to figure out what that means in terms of the change in potential energy that proton goes through, I mean, we can tell its potential energy will change. It's been moved closer to this plate, further from that plate, right? But to actually quantify it, we got to think a little bit more about the situation here. Now, this is the symbol for a battery. Okay, this is how we show a battery. There's a clue there that it says there's a 600 volt potential difference. Okay, now something to note for batteries, they are always shown with the negative terminal being smaller. So the negative terminal is always the small one. So this is negative and this is positive. Okay, and the negative plate, again, if you think about it, what would electrons want to do? Get away from this negative and go into this plate. So this plate is going to have extra electrons. So now we know this plate is negatively charged. This plate, kind of opposite story, electrons are going to want to leave this one, go to the positive terminal, right? And then they'll come out on the other side, get pushed away to here. So this plate is positively charged. Now, if the two plates are connected to a battery with a potential difference of 600 volts, 600 joules per coulomb, that means the potential difference across those plates is also 600 volts, or 600 joules per coulomb. Okay, so we know that to go from here to here, you are changing your potential energy by 600 joules for every coulomb of charge you have. The question we were asked is, what is the change in energy of an alpha particle being moved from here to here? Well, did it move through the full 600 volt potential difference? No, right? But we can see with these lines that they've measured out, it's moved through 2/4 or 1/2 of that potential difference. So it's moved through a potential difference of half of 600, 300 joules per coulomb. So it will change its potential energy by 300 joules for every coulomb of charge that it has. Well, we know how many coulombs of charge that it has. So using the fact that the potential difference is just the change in energy per coulomb of charge, we can figure out what its change in energy will be, right? Take the change in energy per coulomb of charge, the voltage, and multiply it by the number of coulombs of charge. So 3.2 times 10 to the negative 19 coulombs. So plugging those in, I got that its potential energy would change by 9.6 times 10 to the negative 17 joules. I guess we get 3 significant digits here. So let me add a 0. I wrote this as 1.6, but we did know it as 1.60. Okay, so that is its change in potential energy. That's how much the alpha particle's potential energy changed by. But the question now is, did it gain that much potential energy? Did it lose that much potential energy? Or did its potential energy not change? I mean, obviously, it didn't not change. We just calculated how much it changed by. But to think about whether that's a gain in potential energy or a loss in potential energy, right, we have to ask ourselves, okay, so does it have more potential energy here or here, right? And what's important to think about here is that it's a positive charge. So what would a positive charge do in this electric field? Well, it would want to go from C to E, right? If we dropped it, so to speak, it would go zoop, right? So if we take it to here and release it, it's not going to get going as fast, right? Imagine dropping it from here. How much kinetic energy will it get by the end, right? A certain amount. It will. It'll get moving faster and faster. Tells us that it has some potential energy there. But if I take it to here and then let it go, how much kinetic energy is it going to get? Well, none. It's already where it would have moved to because of the electric field here. So by moving it from C to E, we have taken away its potential energy. So this is a decrease, right? It would gain less kinetic energy if released from E than from C. We've moved it closer to the plate that it would naturally move to. The same way if you take a ball that was here and you bring it down to here, right? You've taken away its potential energy. Dropping it from here, it'll get a bunch of kinetic energy by the time it hits the ground. That tells us it must have a lot of potential energy here, because that kinetic energy can't come from nowhere. It comes from the amount of potential energy it started with. But if you drop it from here, it's not going to have as much kinetic energy by the time it hits the ground, right? Showing us that moving it closer to where it kind of naturally would fall to anyway takes away potential energy. All right, next one, an electron moves from A to D. So now we want to think about taking a negative electron and moving it from A to D. Okay, let's actually do this in the reverse order we did the last one. Did we just increase this electron's potential energy, or did we decrease it? Okay, ask yourself, where would the electron naturally go to in here? Well, it's negative. It would go to the positive plate, right? It's kind of actually where it would be. If we lift it to D, so to speak, we've given it a lot of potential energy now. If we were to release it from D, all of that potential energy would be converted into kinetic as it crashed back down to the positive. So we've definitely increased this electron's potential energy by moving it to D. So notice here, right? Don't just assume, okay, moving this way increases potential, moving this way decreases potential. Depends on what type of charge you're moving, right? For a positive, absolutely. Bringing it closer to this negative plate will decrease its potential energy. But for an electron, bringing it closer to the negative plate actually does the opposite. You're giving it more potential energy, right? It's getting more repelled by this downward, and it's going to be attracted to this downward. So you can give it a lot more potential energy at D than at A. Okay, so just summarizing that there, right? And now let's actually calculate what the change in potential energy is. Now, got to be careful here, right? Do we need to know this distance? Does that matter for the change in energy, right? If I were to lift it to here versus here, would I have given it a different amount of potential energy? No, right? It's only how far we move it with or against the field, right? So in this case, okay, we're actually just worried about, it's the exact same as if they had asked us, what is the change in energy to go from there to there, right? The horizontal part doesn't make a difference because moving like this doesn't change your energy. The same way moving a ball sideways doesn't change its potential energy, only moving it up or down does if we're thinking about gravity. Okay, so with that in mind then, what potential difference have we moved it through? Well, we haven't moved it through the full 600 volts, right? But we have moved it through 1, 2, 3/4 of it. And 3/4 of 600 would be 450. So we've moved it through a potential difference of 450 joules per coulomb. We know the charge of an electron. That's also on the back of our formula sheet, so we're ready to calculate. Same equation, same ideas at work, just a different charge because it's an electron now instead of an alpha particle. So that much charge moving through a potential difference where it would gain or lose, in this case gain, 450 joules of potential energy for every coulomb of charge that it has, and that gave me that this electron would gain 7.20 times 10 to the negative 17 joules of potential energy by moving from position A to position D. Right? If it had been going from D to A, it would have lost 7.2 times 10 to the negative 17 joules of potential energy. All right, now it asks a proton moves from F to C. So we know that the proton has a charge of positive E, 1.6 times 10 to the negative 19 coulombs. Ooh, if we move a proton from position F to position C, have we changed its potential energy? You're right, we haven't, right? If we take a ball and move it over here, we haven't changed its height, we haven't given it any more gravitational potential energy. Same idea here, but instead of gravity, electricity, right? We have not moved this through a potential difference, okay? As we'll see in the next lesson, we would say we have moved it along what's called an equipotential line. That's actually what these lines are representing, lines of equal potential, okay? Because they're sideways in this electric field, perpendicular to the electric field. So no change in this case, right? We have given it no more energy or no less energy than it had at F, right? If I release the proton from here, it's going to gain kinetic energy as it crashes into the negative plate. If I do the same thing from here, it's going to gain the exact same amount of kinetic energy as it crashes into the negative plate. So I've given it no more or less potential energy. All right, and another way to look at it, if you want to look at how the equation would tell us the same thing, well, the potential difference between here and here is 0, right? So if we were to plug that into this calculation here, the change in energy would be the charge of the proton times a potential difference between those two positions of 0 volts. Anything times 0, 0. All right, and then D just asks us to compare the electric fields at locations D and B. Well, hang on a sec. It's a bit of a trick question, isn't it? These are parallel plates. What kind of electric field do they produce? A uniform electric field. So the electric field is the same everywhere, right? Parallel plates produce a uniform electric field for all those reasons we talked about. As you move further from the positive plate, sure, its electric field gets weaker, but to make up for that, you're getting closer to the negative plate, so its electric field picks up the slack and gets stronger, so to speak. It's the same at position D and B, and it's the same at positions A, C, E, and F, right? It's a uniform field. It's the same everywhere. And so the last thing it asks us here is to compare the accelerations of an electron and a proton at each of these locations, right? Well, as we've discussed here, the different locations aren't going to make a difference because the electric field is uniform. It's the same everywhere. So at all of our positions, A, B, C, D, E, F, they're in the same electric field. Now, what does that mean for the force that's acting on them, no matter where they are? Okay, well, we know, right, we know that the electric field is just the force acting on a charge per coulomb of charge that it has. So rearranging this, you can see that the electric force acting on it is the electric field it's in times how big its charge is. And so if the electric field is the same for the proton at position A versus position B, you can see that the force acting on it would be the same at position A versus position B, right? If the electric field's not changing, well, the charge of a proton's not changing. So the proton's feeling the same force everywhere, and the electron's feeling the same force everywhere, okay? Now, why are we talking about forces when we were asked to find the acceleration? Well, you know, right? Accelerations are very closely related to forces. In fact, forces are what cause accelerations in the first place. Since the electric field is the force a charge will feel for every coulomb of charge that it has, and the acceleration is just the force it's feeling divided by its mass, right? We can see that the electric field could get us to this acceleration. So starting from this equation here then, right, we can see that the electric force acting on a charged particle is just its charge times the electric field that it's in. Makes sense, right? That's what the electric field tells us. How many newtons of force will it feel per coulomb of charge that it has? So multiply that by the number of coulombs of charge that it has, and you get the actual force that it's feeling. Now, a very common student mistake here is to stop and say, oh, okay, well, I know that an electron and a proton have the same charge. So if they're in the same field, they're going to feel the same force, and therefore they must have the same acceleration. Now, everything that student just said was correct up until they mentioned the acceleration. Okay, because yes, an electron and a proton do have the same charge. Well, one's positive, one's negative. So we should also mention that the forces will be in opposite directions, right? So they do have the same charge magnitude. However, they do not have the same mass. Protons are much, much heavier than electrons, about 1,800 times heavier. So Newton's second law, right? If you apply the same force to a larger mass, you don't get as large of an acceleration. So really here, just actually applying physics principle number 1, accelerated motion, Newton's second law, right? That's all we're thinking about here. We're saying that the acceleration of an object will be equal to the force that's acting on it divided by its mass. Now in this case, for the proton and the electron, the force that's acting on them is the electric force, right? And for each of those, we've just shown that the electric force is just Q times the electric field they're in, right? So we can replace Fe in our equation with Q times the electric field divided by the mass. And this can let us see how the proton and the electron's accelerations will compare, okay? Because this is the expression we would use to calculate both of their accelerations. We would just be putting in potentially different numbers here for electron versus proton. So let's go through one at a time. Q, the charge. How do they compare between a proton and an electron? Well, they're both the same number that we would put in, right? But we have to remember one is positive and one is negative. So what that means is they would feel the same size force, but the electron would feel a force this way because it's negative, while the proton would feel a force this way because it's positive. So let's just mention that, but Q is the same number. We would put the same number in for Q, 1.6 times 10 to the negative 19 coulombs. Now, they're both in this uniform electric field, so that's the same for both of them as well, right? The electric field is just, if we knew the distance here, we could calculate it. We don't, but it's uniform, and it just goes in this direction. Now, that electric field will cause an opposite direction force for the proton versus the electron, right? Again, electric field is in the same direction that a positive charge would feel a force, right? But that means it's in the opposite direction as a negative charge would feel the force. However, it's the same size, so they will feel the same size force just in the opposite direction, okay? Because they're in the same electric field. And now the last piece of this equation here, as we think about the acceleration of the proton versus the electron, our numerator is the same for both of them, but the denominator is not, right? And so their accelerations will not be the same. M, the mass, is much larger for the proton compared to the electron, right? Just from the back of your formula sheet, the mass of a proton, 1.67 times 10 to the negative 27 kilograms. Mass of an electron, 9.11 times 10 to the negative 31 kilograms. This is much smaller number, just to compare them, right? By dividing to see how many times bigger, about 1,800, like I said, times larger proton compared to electron in terms of mass. So, right, we've established that they feel the same force because they have the same charge and they're in the same electric field. But does the same force have to mean the same acceleration? Absolutely not, right? If you push something that's 1 kilogram with a certain force, and then with the same force you push something that is 1,833 kilograms, which of those two objects is going to change its motion more, right? The smaller mass. It's much easier to change the motion to accelerate a smaller mass than a larger mass. That's just Newton's second law at work. So to summarize, we were asked to compare their accelerations. Here's what we found. Since we are dividing by the mass in the equation we built here to find acceleration, and the mass of the proton is 1,800 times bigger, right? We're dividing by a much bigger number for the proton than for the electron, giving us a much smaller acceleration for the proton than the electron. Okay? And also, we should mention, we're talking about acceleration. That's a vector. So since we're comparing them, a good way to compare them is also their direction. So also, they will be in opposite directions, right? The electron will accelerate downward towards the positive plate. The proton will accelerate towards the top of the page towards the negative plate. So we'll add that. And there we go. Okay, so that wraps up Chapter 11, Lesson 2. To be honest, if you took those little work breaks and did the practice there, I think you've actually done the entire practice assignment for this lesson. But if you got any left, try them out, see how they go. As always, the solutions are posted, and I am always happy to help. So if you're struggling with anything, don't be shy to reach out by email, book a meeting, or whatever you prefer. But there we go.